Our first example asks us to approximate the sum of this series by using the first four terms and explain why our estimate differs from the actual value by less than 1 over 100. Then use your results to find an interval in which s must lie. So let's break this down into reasonable sections. Let's approximate the sum using the first four terms. Alright, so the sum is approximately equal to the first four terms. It's going to be negative 1 to the 0 over 1 factorial plus negative 1 to the first over 2 factorial plus negative 1 squared over 3 factorial plus negative 1 to the third over 4 factorial. Alright, and that is equal to 1 over 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial. And using my calculator, I figured out that that is 0.625. So our estimate for the sum using the first four terms is 0.625. Alright, so we basically want to look at the fifth term, right? We know that our s sub 4 is equal to 0.625. Alright, and our error, or our remainder, is going to be less than the magnitude of the fifth term. Alright, and this is the true sum minus our fourth partial sum. Sorry, these are still equal. These are just all different ways to say the error. Error, remainder, the true sum minus the fourth partial sum is going to be less than the absolute value of the fifth term. Alright, so the fifth term is going to be, the absolute value of it at least is going to be 1 over 5 factorial. So that's 1 over 120, and that is less than 1 over 100, which is what they asked us to justify. Alright, so we're using this alternate series remainder theorem, and we have to justify its use. So this series that we're looking at has to be an alternating series. So we have to justify its use by stating that the terms alternate. They decrease in value, in magnitude, sorry, not in value, in magnitude. And they have a limit of 0. Right, so we know that we're within 1/120th of the true value. Right, so if I take that 0.625, sorry, and I subtract 1 over 120th, my true sum is going to be between there and 0.625 plus 1 over 120. Alright, so the interval that I know the true sum falls within, I know the true sum is going to be somewhere between 0.617, which is what I get here, and when I add 1 over 120th, I get 0.633. Alright, so I estimated the true sum by using the fourth partial sum, which I got to be 0.625. And I know that my error is going to be less than the absolute value of the next term that I didn't use. So since I used the first four terms, I'm looking at the fifth term. The fifth term would have been 1 over 5 factorial, which is 1 over 120. So that's my justification for the fact that my estimate differs from the actual value by less than 1 over 100. I have to justify that using the three conditions that I do have an alternating series here, a converging alternating series. And then I know at 0.625 I'm at least within 1/20th of the true value, so I add 1/120th and I subtract 1/120th, and I know that the true value is going to be somewhere in between there. Alright, let's look at the next example. It says, what is the fewest number of terms needed to approximate the sum of this series so that the estimate differs from the actual sum by less than 1 over 1,000th? So here we're kind of specifying our accuracy requirement. Then I'm saying, okay, well, how many terms am I going to need? Right? If I list out the first few terms of this sequence, I'm going to have 1 minus 1 over sorry, I need to change this. I just copied this from the above example and I shouldn't have. This one needs to be negative 1 to the n plus 1 over n to the 4th. I'll switch that on your notes, so by the time you see these notes, when you print this out, it should have the correct series in there. But we're dealing with negative 1 to the n plus 1 over n to the 4th. So the first few terms, I have when n equals 2, I'm going to have 16 here. When n equals 3, I'm going to have 81. And then my last one is going to be 1 over 1,296. So you can see that this is the first term whose magnitude is less than the error requirement that I've been given, right? So I know if I just use these first 1, 2, 3, 4, 5 terms, then I'm going to be within 1 over 1,296th of the true sum, which is less than 1 over 1,000th. Right? So I can say that 5 terms are needed. Because this series has terms which are 1, alternating, 2, they're declining in magnitude, and 3, they have a limit of 0. Right. You could also do this algebraically. If we look at just a of n, so we omit the alternating part, and we just have 1 over n to the 4th. That's a of n. All right. We want that to be less than 1 over 1,000. So n to the 4th has to be greater than 1,000, and for that we get n needs to be greater than 5.623. So that means that the 6th term will be less than 1 over 1,000. So we'll need 5 terms. So that's kind of an alternate way of doing that problem if you want to use a more of an algebraic approach, just looking at when will the next term, that a sub n term, be less than 1 over 1,000.